Good morning, good afternoon, good evening, wherever you are in the world. Welcome to my show. My name is Diana Hooper, and I'm a theoretical physicist currently based at the University of Helsinki, where I'm doing a postdoc, which is somewhere in between being a student and being a professor. And my focus is cosmology. That means that I study all the fun things happening in the universe, like dark matter, dark energy. I don't actually work on dark energy. All of the crazy stuff happening inside the universe. It's a great topic. I love studying cosmology, and I love jumping here on Happs to talk to everybody about all of the wonders of the universe. It's so much fun. Hey Scott, great to see you in first today. Glad you could join. So today we're going slightly off topic for me. We're not going to focus on cosmology, and instead we're going to focus on possibly one of the strangest things within the universe, so one of the strangest things we've been able to actually measure, which is the idea of quantum entanglement. So quantum entanglement is a very odd topic. You might have heard of it. Today is your chance to ask any questions. And because this is a very, very difficult topic, I'm not going to be discussing this alone. I have someone here to help me. So I'm very happy to welcome Haley up on screen with me. Hello and welcome to the platform.
Hello, great to be here.
Great to have you here. So do you want to introduce yourself to everyone?
Yes, I'm Heli Takkoan. I'm very fresh, very new PhD student at the University of Helsinki, working in quantum information, studied entanglement, done maybe focusing on something else as well, but entanglement, I believe I'm a bit more familiar than Diana.
Yeah, definitely. It's something that I touched in my bachelor, in my undergrad. I studied entanglement, and I've never needed it. It's one of those things that is fun, is useful to know of. I've needed it in some presentations I did on quantum entanglement, but it's not something that affects my day-to-day work. So it's definitely fun to have this conversation. Just want to say hello to David here in the comments, and thank you for the high award. I always do appreciate the awards. They do mean a lot. So before we jump into quantum entanglement, what is the point of entanglement? Okay, I see we're already getting into those questions. We'll come back to what is the point of entanglement soon. But before we get into that, and hello Molly, thank you for joining. Before we get into what is entanglement, we should probably start with what is quantum mechanics. So Haley, can you give us a very brief summary? What is quantum mechanics?
Yes, it's really successful theory, really that can explain one of the really the smallest things happening in our universe, and something that is not explainable with classical physics. And that's really the kind of definition of quantum mechanics, is that we can explain things that aren't really happening in our day-to-day life in the scale as we know it, but are happening in the level of subatomic particles. And our classical mechanics cannot explain it, so quantum mechanics really is the thing that we have developed and found essentially to explain those kind of systems and processes.
Yeah, so quantum mechanics allows us to understand the very, very tiny world. It's like when you start studying physics, you're told objects have a position, they have a velocity, they have, a clear cause and effect. And then you actually learn, no, in quantum mechanics, this only applies to big objects like us, like cats, like universes, like galaxies. But when you look at what particles are doing, you can't actually say the particle exists in this specific point and the particle has this velocity. It becomes a bit messy. Everything becomes a bit fuzzy. And as Hilly was saying, at that point, classical mechanics breaks down and we need to switch to quantum mechanics. Yeah. I just want to say hi to Swift Beach joining here. Thanks for joining, Swift, and thank you for the high award. Please go ahead, Hilly.
One thing I really find interesting is that, for example, light is something that physicists early on have studied with using classical mechanics and found that it's not really working, and then quantum mechanics came along. But really some of the certain equations and certain things that describe quantum mechanics can be generalized to classical mechanics, setting some parameters equal to 1 or setting them to vanish. So it's not really detached from a real world. It really is just like continuation of the classical mechanics, because it only can describe so much.
Yeah, it's not one or the other. You do need both to understand
Yeah.
different scales of the universe. I just want to acknowledge a comment that David has made here in the comments, where you sent me the high award and said the high is a wave, and in this context, perhaps it's also a particle. So I appreciate that comment, and that does allow us to make the point that when we're dealing with quantum mechanics and we talk about a particle, one thing to remember is that every particle is also a wave. So we know that particles will travel both as a particle and as a waveform as well. And this leads to some very, very fun phenomena, like particles interacting with themselves in the waveform. You can have one particle that interacts with itself because its wavelength or its waveform would interact with itself. So we do have this idea that particles can be both a particle and a wave, and this is one of the main tenets that we need in quantum mechanics. And that gag pretty much exhausted your knowledge of quantum mechanics. Well, hopefully by the end of the stream, we can extend your knowledge of quantum mechanics a bit more. So one idea that we need for quantum mechanics is this idea of superposition. And I was already hinting at it here with the idea of particle and wave. Do you want to tell us a bit about superposition and what it is?
Yeah, really, I actually think it's very nice and beautiful thing, because in classical mechanics, when you need to describe something that it's called many body problem. So you can have planets or something, and you need to describe the system according to all of them and take into account the interactions between all of them. But in quantum mechanics, the superposition really means that when you think of this kind of many body system, that you have many things, many particles, for example, in your system, you can describe the whole system as a essentially sum of those individual systems, and it adds up, which is really helps you, because in classical mechanics it gets really messy really fast.
Yeah. So one way to think of superposition is, as Kelly was saying, it's just all of the possible states superimposed. And I think one way that we can really explain superposition is by using one of the main experiments we have to test this, which I'm just going to bring up on screen. The idea, wrong button, this one here. The idea of there it is, there's the image. Happs is slightly slow in reacting today. So what you can see here on the screen is the idea of the double slit experiment. So here we're just shining a beam of photons, which are particles of light, through a single slit. Here it will behave as a wave, so the photon will travel out as a wave. Then we have the double slit experiment. So we have two slits here. And Haley, if I say anything wrong, please do feel free to correct me. You know more about this than I do. So in the double slit experiment, we have two slits, so two holes. And this photon beam travels through both. Now, as it does this, because it's traveling as a wave, it's actually going to interfere with itself. And I'm just going to take us off screen for a sec to make this big. And what you can see here is when you measure at the end where the photons end up, you have this kind of interference pattern. You see dark areas and light areas. And this is just sending several photons through. And the idea is all photons will travel through all possible paths at the same time. And at the end, they will go where there's the interference, where the constructive interference of the waves, so where all of the waves meet. The fun thing is that if you actually look at the double slit, so if you put a detector to measure which of the two slits the particle is going to take, what you will actually see, instead of this multiple bands of light and dark regions, you will just see two bands of light and dark regions. Because if you measure where the photons go, they will choose to either go through one slit or the other, and you will measure this. But if you take away your measuring device, the photons will travel through both slits at the same time and interfere with themselves. The idea here with superposition is that this photon exists in all possible states at the same time. It takes all possible travel paths, even the one where it goes off to the shop on its way through the double slits. It takes all possible histories, and then they superimpose. When you observe, you collapse this into one possible path, and then it's determined what it's going to do. But until you make that measurement, the photon travels through every possible slit.
Yeah, and actually something very interesting, if you look at the screen in the end, you will actually see that some of the positions are more likely than the others, but you will have some sort of probability in all of the screen, but yeah, you have somewhat higher probability of the particles to be found in the middle than in the edges. And I think that's very interesting, and also it was used to prove the particle wave duality.
Yeah, so there's a lot hidden in the double slit experiment because it allows us to show that particles behave as both a particle and a wave. They behave as a wave until we observe them, and then they behave as a particle. It also allows us to see that making a measurement affects the outcome. Because if you don't measure which hole or which slit the photon is traveling through, it will travel through both in a wave form. If you make a measurement, it will travel through one or the other as a particle. So here we can see superposition, we can see the idea that making a measurement affects the outcome, and we can see the idea that particles have both particle and wave. So what does measure mean here? What is the difference between a detection and the particle just hitting the screen? Right, so this is a great question, David. Do you want to answer this, Helly?
Yeah, it's if you would shed a light through that, and that of course we know is many particles, right? And if you would think it only as a like one particle that you shed through, you would also get a similar kind of probabilistic result on the screen. But measuring exactly one, only taking like single one in, it will hit somewhere in the screen, and it will not give you this kind of probabilistic distribution. I feel like I didn't explain anything.
No, I think what you're saying makes sense. Just to add to it here, so I think we were mixing terms when speaking as well, and saying about measuring and detecting. So on the screen here, you're always going to have a pattern of photons, of particles that are going to hit the screen. It's basically a piece of metal, and you measure where the particles of light hit. Now, on the other hand, when we're talking about making a measurement, what we mean is at the place where you have the two slits, you can put a device to check which of the two holes the photon is coming through. And if you have this device here at the double slit place, instead of seeing these 5 bands at the outcome, you'll just see 2 on the screen, because the photon will either travel through the top slit or the bottom slit. In this case, it travels as a particle, and it can no longer interfere with itself. So just by putting a measurement device at the point here where there's the 2 double slits, you change the pattern you get on the screen. So by adding this, go ahead.
No, that's also known as collapsing all possible states into the one that happens at that time.
Exactly. So when something is in superposition, as we were saying before, it occupies all possible histories, all possible states. And we call this the waveform. Now, when you make a measurement, you collapse the waveform. So instead of having all possibilities, it's collapsed to one, the actual realization. So what changes is the appearance on the screen. And what we're adding is some type of observer or measurement device at the position of the double slits. So this determines whether the photons will travel through as a particle or as a wave. I hope that answers your question, David. If not, please do feel free to ask us again, because we are going to try to explain it as best we can. And we know that quantum mechanics is a very complicated topic. You can study it for years and still be very confused by it. I think everyone is to some degree confused by it.
And
so
the reason
it
is so confusing because by definition, it's not something that we encounter in our day-to-day life. So classical mechanics, you can push the ball and see where it goes. But quantum mechanics, really, you need to learn the word logical and intuition again in this field.
Yeah, so it's definitely something that is confusing. So if anyone's confused, don't worry, you're not alone, and do feel free to ask any questions you have. And as always, remember, there are no stupid questions. You can ask whatever you want, and we will do our best to answer them. We don't have all the answers, but we're going to do our best. So yeah, the idea here is we wanted to remind everyone we have this particle that travels as a particle and wave. We have superposition, and we have the idea that making a measurement collapses the waveform, and then you're no longer occupying every possible space, but you have a clearly defined outcome. No stupid questions? Yeah, go ahead, Scott, try us. You can't ask stupid questions. Still doesn't make sense how it can be something real. Yeah, it's like, how can it be real that making a measurement changes the outcome, right? This is something that is difficult to wrap your mind around, because we're used to objects having a physical space and behaving as we would expect them. As Helly was saying just now, if you kick a ball, you know what's going to happen. But with particles, everything becomes a bit messier because we are talking about these tiny, tiny things. It's like, it's very hard to say, look, here's a particle, because a particle exists in many different positions at the same time. And this makes it very difficult to actually conceptualize and to actually visualize what is going on here. The double slit experiment is one that has been repeated hundreds of times. It's one that I had to do in my undergrad. It's super fun. I'm not sure if you ever had to do it, Helly.
Yes, multiple times.
Multiple times. And it's always super fun because you actually see this happening and you're there like, this makes no sense.
I mean, imagine the people who first made this, like, let's try to do this in experiments, and they get this really weird result. How do you even start explaining that? It's, I think it's amazing.
Yeah. So at least now we kind of know this, but the first people doing it, they must have been so confused. So, Scott, to answer your question, I'm still going with the idea, no stupid questions. Quantum mechanics applies only to small things. We can't use quantum mechanics to explain the behavior of people or of big objects. So, quantum mechanics cannot help you understand things like that. Okay, so I think we're done with the double slit experiment. Is there anything else you would like to mention of the double slit before I take it off?
No, I think we should aim to the entanglement next.
Perfect. So we've covered some basics, just set the groundwork. So now the big question, what is quantum entanglement?
By definition, a short definition as I can give, it means that you have two particles or two states or two systems, and you cannot describe one of them without the other. Meaning that you cannot, it's like they come in pair, like shoes. But interestingly enough, it actually is not tied to only two particles. For example, you could construct a system with 3 entangled particles. So it's not only in pairs, even though that's the most used example. And yeah, do you want to say something?
Yeah, no, I was just about to say that, yeah, we usually do pairs because it's easier to imagine and to visualize, but there's no reason why it should be. So there's one example that I've used in the past to try to explain quantum entanglement. So we are having the idea here that you have two particles that have something shared. So they are connected. The basic example that people always give is the idea of particles with spin up and spin down. So the universe sometimes can just spontaneously produce particles. Out with a vacuum, you borrow some energy, you produce particles. Now, we know that angular momentum, which is like the total rotational energy of a system, has to be conserved. So when you produce particles, if one has angular momentum in one direction, the other one will have opposite angular momentum. Now, we often describe this as spin up and spin down, just as a way of thinking about it. Now, you can produce these two particles, or the universe produces these two particles. You have your spin up, spin down. But until you make a measurement, as we said before, the particles exist in a superposition. So both particles are both spin up and spin down. And as soon as you make the measurement, you're going to collapse the wave function and decide if it's spin up or spin down. Now, because you have these two particles that are linked, you know that one is going to be spin up and one is going to be spin down. Until you make a measurement, they are both in a superposition of up and down. And now say you measure this one over here and you find that it has spin up. Immediately, no matter how far away it is in the universe, the other one is going to be spin down. You can measure it 100 times, it's going to be spin down because it's already been determined by measuring the first one. This is very weird when you think about it. This is what is known as spooky action at a distance, or quantum entanglement. The reason it's spooky is because you don't expect particles that are really, really far away to be able to affect each other. And yet somehow they do. I just want to acknowledge some people here. Hey, Abyss, thank you for joining. It's really nice to see you. Don't worry if you can't stay. You can always catch a replay. It's great to see you again here, Abyss. For another occasion, can you explain what spin and angular momentum means? Do we want to go into spin and angular momentum now, or do we save that for a future stream?
Because the thing is, spin is usually meant something like it's really nothing. It's a property of a particle, and that's the most correct way of describing it.
Yeah. So we call it spin just because it helps us, but it doesn't actually mean the particle is spinning. In the same way that we give particles colors and flavors, it doesn't mean it has a specific color or a specific flavor. It's just a word we use to define one of the properties that the particle can have. So there's a question here by Joel of, are we saying that measuring two particles is what creates the link? Do you want to take that, Haley?
It doesn't create the link, but it reveals the link, essentially. And it really reveals kind of, again, it's, you collapse it and you measure it, and then you see like, okay, what's the result? But we can already, before we measure it, we can know if there is entanglement or not. And because measuring the system, as in collapsing the wavelength, is a wave function, is not the only way of seeing is there entanglement or not. So the link is there already before we measure it.
Yeah, so that, I think that's a really nice way of explaining it there, that we're not creating the link, we're just showing that there is a connection between these two particles. Now, this is something that was initially proposed many, many years ago, and it's something that didn't sit right with everyone, namely with Einstein. Now, Einstein's general relativity tells us that nothing in the universe can travel faster than light in a vacuum. This is one of the truths that we know in the universe. It's one of the few things we're pretty sure of. But now if we have these two particles, imagine they're created here, they're entangled, and you send them off in opposite directions, they travel for thousands of light years, or for thousands of years, sorry, and then you do this measurement. Now, when you measure one, the information is instantaneously at the other particle as well. And Einstein asked the question of, how is this information being sent? Because is this implying faster than light travel? Because we don't like this faster than light travel. It shouldn't be allowed. So, question for you, Haley: do we violate this? Does information travel faster than light when we have
no information? Really, it does not. It cannot. There is no way it could ever travel faster than light. And the key to this kind of information paradox when talked about entanglement is that there is no traveling happening in any case, because they are already described as a one system. And so you don't send any information. The information is already encoded to those two states, and it just reveals them when you measure it. So you don't send any information from one particle to another. You just open the box and see, okay, this is the result.
Yeah, this is the outcome. Can a particle in my room be spontaneously entangled with one in your room, or do they need to be near each other to become entangled? I'll pass that one to you.
Ooh, that's actually very, I don't think it does not need to be near one another. So a very famous example is that you have particle here and you have another one on the moon. But it actually has been studied that you might be able to create entanglement if your particles have overlapping wave functions in space or time. But it's not required for that.
So that is very curious to me, because always when I think of entanglement, it's like you create particles together with this entanglement and then they travel apart. But they don't need to come together at any point. You can actually create entanglement without them being in contact.
Yeah, because then you would have to be able to find kind of spatial limits in, like, if you enter, as in like black hole horizon, once you enter there, you're in. Like, you would have to define some sort of limits, and there is no such thing.
Yeah, so then it makes it even more fun that you can just have particles that are entangled even if they never came together. So they need to have overlapping wave functions?
They don't need to have, but because the one and big question for physicists and why we want to be able to get a grasp of entanglement and be able to actually create entangled systems so that we have them all figured out, because I mean we can discuss later how that will help us and why is entanglement such a big thing and why do we want to know about it. But that's overlapping wave functions is one candidate for us how to maybe create entangled particles, but it's not required for them to be.
Yeah, and I think it's important that later on we will come back to why we care about entanglement, because it is a very interesting question, and we will come back to that later. But going back to this idea of quantum entanglement, we have these spooky action at a distance. As Haley was saying, it doesn't violate speed of light. So then we can come to several different interpretations of this result. Now, Einstein proposed that the system actually has hidden variables. So that imagine you're creating two particles together with opposite spin, because spin is useful to visualize things. So what Einstein was saying is that there's some hidden information that we can access, telling the particles how to behave if they're measured in different ways. So, not necessarily telling them you're going to show spin up, but just containing all of the relevant information so that when these measurements are made, the information does not have to travel. Then there's the other interpretation, which is what Bohr liked, which is the idea that actually, the universe doesn't necessarily exist when it's not being observed. So there's no hidden information. It's just that the universe has this randomness to it. It has these random elements, and it's going to decide what happens, and the information is going to be instantaneous looking at the other particle. We have actually been able to do experiments to confirm which of these two ideas is correct. And that leads us to the Bell experiment. And I think you wanted to discuss the Bell experiment as well, Helly.
Did I?
Okay, so just the idea of like how do we measure quantum entanglement? Let's start with that, and then I'll go into Bell inequality.
Yeah, well, for me, how do you measure quantum entanglement? First thing, you may ask, how do you prove quantum entanglement? And that's something you can measure particles like photons and see that they cannot coexist in time or space without one another. Or if you measure electron and its spin and you see that the other one exact the same time is the opposite spin. Those are the kind of proofs. What kind of probes do you use to measure it? The most famous and useful is entropy. And I think most people, when you say entropy, they think about the universe and the amount of chaos somehow. But I would describe it as the amount of information we have of the system and the amount of things we don't know about the system. And when you think about entropy of entangled system, the bigger the entropy is, the less we know about it. And that's something you can actually, first of all, you can calculate it. We can come back to that later and discuss how easy it is to calculate it. But also that's something that you can measure with, for example, using really, really kind of easy probes as temperature or such. But I'm all for entropy. We have also other things depending on the system that we consider, for example, quarks and their confinement. They come in pairs. That's, I think, very also another interesting discussion. Why is that so? But in those cases, the potential between them, you can link that to the entanglement. And yeah, entropy is the biggest at the moment.
Yeah. So there's a lot of ways we can measure this. It's something that we have measured, that this entanglement does exist. And I want to go to David's question here. So it's not just that one is deterministically up and one is deterministically down when you measure. Do you do something like the slit experiment to prove they are ways before observing and collapsing it to just up or down? So this is a nice question. The idea here is that the first particle you measure, its spin is random. Until you make the measurement, it could be up, it could be down. It's in a superposition of both. So you don't have one that is already up, it's known to be up, and the other is known to be down. Rather, they are both. And it's not until you make that measurement that you're actually able to collapse the wave function. And this automatically determines the outcome for the other. Now, we're just glossing over a lot of details here about how you measure this spin. And we're saying like spin up, spin down. And this assumes you're measuring in this direction. But you could also have your particles along this direction. And then you have spin left, spin right. And if a particle is entangled in the up-down direction, all it's telling you is that if you measure it along this direction, one will give you up, one will give you down. But if you measure it in that direction, you might not get the same answer. And then it becomes a game of probability of whether you get up or down. So this is a way we can test that the particles are behaving randomly. Imagine you generate 20 pairs of entangled particles. Some you measure in one direction, some in the other. Now, the ones that you measure in the direction along which they were entangled will give you this entanglement. Whereas if you measure in another direction, you won't find this entanglement. So you can measure this wave nature as well. And I just want to mention about Bell's inequalities here. So with this idea that you can measure along different directions, Bell came up with the idea that you can actually calculate statistically how frequently you should find overlapping protons and how frequently you should find ones that give different results. Based on this, he proposed some inequalities and basically said, if these inequalities are violated, so if we don't fulfill this inequality, it means there is no hidden information in the system. There is nothing there, as Einstein was saying, some hidden variables that we just can't know. And every experiment we've been able to do so far has shown that Bell's inequalities are always violated, which means that there is no hidden information. So this idea that Einstein had to try to make sense of quantum entanglement, that the information is already contained in each individual particle, is not actually the case.
Yeah, that was the famous saying that God doesn't play dice, and seems like universe does. So
yeah, Einstein said God doesn't play dice, but the universe said, actually, yes, I do.
Yeah.
So that is fun. And then we come back to the idea of what does this mean in terms of violating the speed of light. And this is what Haley was saying before, that we're not sending the information. The information is just drawing because we need to consider the system as one wave function. So if it was one wave function in one place and one wave function in another, then you would be sending information. But because it's the same wave function describing both particles, you are not sending information. This actually comes to the point that Scott is making here in the comments, which is actually not a bad idea here, Scott. A lot of people have asked if we can use quantum entanglement to send information faster than light. I'm going to pass that one to you, Haley.
Unfortunately, that is not possible, but kind of like second prize would be that you can send more information than with entanglement than with the normal computers. So there is something to it, but unfortunately, the speed of light seems to be one of the few things that we can really trust in life.
Yeah, so it is nice to think that, you know, we could send information here, but there's really no sending of information. And this is something that is important to remember with quantum entanglement. The particle is not like calling up the other one like, hey, so I'm up, you have to be down. Right? The information just already exists in both places. But it is the avenue that a lot of sci-fi shows take of let's just throw in quantum entanglement for faster than light communication. But unfortunately, it just doesn't work like that. Just want to say hello to the Broadcast Advocacy. Thank you for your nice comments, and thank you for subscribing. It's great to see you here. So unfortunately, we can't use quantum entanglement to send information faster than the speed of light because there's no sending information. But I think we can go on to the question now of what can we use quantum entanglement for?
I love this question because also that's something I use first of all for grant applications, but also kind of motivate myself. Why am I so interested in this field? And it's very, very current in our world. And I don't think people might maybe realize that it seems so distant and so spooky and random, but really quantum computers are the biggest one at the moment. The reason why entanglement is such a big thing and why is it so important. Quantum computing, meaning you have qubits, quantum bits instead of bits, which are really just that kind of superposition of you have those two states and they can be either 1 or 0, which is definition of a bit, but at the same time. And you can store much more information to that one qubit than to one bit. And the amount of information you can store and the amount of power you can extract from those qubits is exponential compared to the normal computers. So obviously that's already one very big motivation. Another aspect is quantum cryptography, which really is trying to, well, you would make a lot of good sci-fi movies from this topic, I think, because it's fairly close to real life, meaning those kind of quantum algorithms that could exploit the entanglement in order to crack cryptid something is I think very possible in the future. And just in general, anything to do with computing, it's going to be very, very different from the normal one using entanglement. Then something a bit nicer and not that scary is very fundamental physics and particle physics, understanding how quarks really work, what's the deal with them, why are they confined, and you can use entanglement measures perhaps to help that. For example, photosynthesis is something that has been proven to work with the help of entanglement, if you can put it that way.
Okay, I want to know more about this. Okay, that's something to look up there, because that's really cool. So photosynthesis is the process by which plants basically use oxygen or produce oxygen from carbon dioxide. I did not know that you could connect that to quantum entanglement, and I want to know more about that. So I will ask you about that again in the future. But yeah, I think it's really. Did you have other things you wanted to mention of uses? I interrupted you there because I got distracted by photosynthesis.
Yeah.
Yeah, go ahead. Let's see what else can we do with quantum entanglement.
No, I really want to like almost go through and cross the line between, like, I want to go to the talk about holography, but I think that's a topic for another day.
No, we have time. Let's go into it. So I was going to ask you at some point, can you tell us what you're working on? So what is holography? Yeah. What does it have to do with quantum entanglement?
Yeah, so as I was saying, we can discuss how easy are some things to compute when we want to measure entanglement. And turns out it's really hard, especially if you want to keep on working on the quantum field theory side. And holography is something that discovered there are dualities or analogous theories on the gravity side to some of the quantum field theory sides. So turns out you can describe states of quantum system with gravitational theories such as black holes. And it's a mathematical trick, essentially, and it doesn't apply to all quantum theories, just a certain one. So it's small group, it's not theory of everything, but it could be the theory of entanglement. That was very poetic.
I have myself muted there. No, I think it's nice. So holography basically, or I say basically, but it's a mathematical trick we do to make things easier to calculate, right?
Yeah. And it means I calculate entanglement entropy using black hole geometry and general relativity.
So that's a big statement, a lot to unpack there. So can you tell us what that means? Like, how do you use black holes to measure entanglement, and what's the connection here between black holes and entanglement?
Yeah. So when you have entangled state, you can think about those two states as mathematical spaces. You have some sort of mathematical description of that state and the mathematical space. And it turns out you can do a reduction so that those dimensions of the system match system in a gravity side on the boundary of that entangled area. And you say that the field theory lives on the boundary of the bulk space-time. And then you can basically just use the mathematics of that gravitational theory, because you have reduced your mathematical space to match the one on the gravity side. And all of a sudden you are only working with gravitational theories and probes and equations, which you might surprise are easier than the ones in the quantum field theory.
Somehow.
I've
heard a lot about holography, and every time I do, it just seems magical to me. It's like we take these complex systems, we do some mathematical tricks, and suddenly everything's a bit easier to calculate. It's still very difficult to calculate, but it's just a bit easier.
Yeah.
And I think that's so cool.
Yeah, and for example, when it comes to measuring entanglement in that system, measuring entanglement entropy, which reveals how much those two states are entangled, essentially, is impossible in most of the interesting cases that we want to calculate, because the integrals, you can't calculate them. They're just way too complex, way too hard. And once you do this reduction to the gravity side, you see that, wait, this integral I can do, and it gives you the entanglement entropy of that system.
Nice. So we can go back to the question we had at the beginning of like, what's the point of studying quantum entanglement? And I think you've given us a lot of reasons here. Of course, there's a reason because it's fun, because we can. because it's something about the universe we don't understand, or we think we understand somewhat. And it has a lot of applications, like making our math. Somehow, this spooky action at a distance can be used to make other things simpler to calculate, which is ridiculous when you think about it.
Yeah.
But super, super fun. So one direction we can go with the conversation of quantum entanglement, because there's a lot of things to explore with quantum mechanics. So a question from David here: if I entangled two particles and bunged one into a black hole, could I then observe what is happening in the black hole as anything in there that collapses the waveform affects the particle outside? That is an excellent question.
Yes. Oh, that's very fun question. Also, very nice thought experiment. But unfortunately, entanglement only reveals properties that the system already has, and those properties might not be dependent on the surroundings of that particle. So if you want to know what happens inside the black hole, it doesn't really help you to send there a particle with spin up, which you already know has a spin up if you measure it otherwise. So knowing a spin is up inside the black hole, it's something you already know without sending it to a black hole.
Yeah, and I guess the other thing you could think here, you have the spin up, spin down, you don't know which is which, you send one in the black hole, you keep one to yourself. Then if you measure the one outside and say it gives you spin down, it doesn't tell you if something inside the black hole measured spin up, or if you're the first one to measure spin down and therefore the one inside is spin up. You can't know if the waveform has already been collapsed inside the black hole, or if you're collapsing it with your measurement. So it's a super cool thought experiment there, but I don't think you would gain any information about what's happening inside the black hole or the surroundings or anything, just because it goes back to what we were saying before, that these entangled particles don't carry information. It's just the information that they already contain. So,
yeah. But this is something also in like quantum cryptography maybe, is that if we find a way to solidly create entangled pairs, you can think of it a particle on the other side of a crypted quantity, and then the particle that you have on your available on your computer screen without any crypting, and you have a way of entangling those particles. You know if that qubit is then 0 or 1, and essentially you know the information on the other side of that crypted. So something like that is very huge if you can figure out a solid way to create entangled particles and control them.
Yeah, and I want to go back to a somewhat jokey comment that Scott was making before. So Scott asked how accurate is anything in Ant-Man movies where they go into the quantum realm, and shortly, absolutely nothing.
Yeah.
But it always surprises me because sci-fi shows take really weird approaches, like the quantum realm, let's shrink ourselves and go there. And they don't need to, because quantum mechanics is already so crazy. There's already so much you could do that's physically real. And instead they do weird things like let's just shrink people into the quantum realm.
Yeah.
So I think it's underappreciated just how much fun you can actually have with like quantum cryptography, for an example. You could write a whole sci-fi show about that.
Yeah.
And it would be much more fun.
I think there was also a question that, Diana, why don't you use holography in your own work?
Yeah, that was a nice question by David. So holography itself, I'm not sure how it would relate to dark matter. I'm not sure what we could do with holography and dark matter. As to why I don't use entanglement or quantum mechanics in general. Now, generally, when I study dark matter, I'm looking at the whole system or the whole species that is dark matter. Now, we don't know what dark matter is, but if dark matter is made of particles, then each individual particle of dark matter will also be subject to the laws of quantum mechanics. Hey, Paul, thanks for stopping by. So nice to see you. Hopefully, you can catch the replay as well. So if you took an individual particle of dark matter, we assume that it would obey the same quantum mechanical rules as normal matter does. But when I study dark matter, I don't take one particle of dark matter, because what I'm interested in is how dark matter affects the overall things happening inside the universe. Like, for an example, and I'm not going to pass up this chance to do this, like, for an example, how dark matter affects the CMB, the cosmic microwave background radiation. And for things like this, you don't need quantum information, you don't need quantum entanglement. Just to feel so you know why I did that, Haley. There's a running joke that I can't spend a single stream without flashing the CMB. So I just found an excuse to slip it into the entanglement discussion. Yeah. Thank you for that.
And to be honest, the reason I don't think Diana would benefit from holography is that holography really helps you when you want to solve something in the quantum field theory side, but it's too hard. And that theory happens to be analogous to a gravity theory. So gravity and gravitational equations and mathematics in this case are easier than the ones on the quantum field theory side. So why would she jump from the easier side to the more complex? It won't help her. You're already there.
I'm already doing the easy math.
Yeah.
It doesn't feel like the easy math, but yeah, it's the easy math.
Imagine people running into like integrals in the field theory side, and they are like, okay, these are so hard, we need to come up with a new theory to calculate these. That really what happened.
Yeah, we're still trying to figure out what dark matter is. We don't need so many complicated equations that we would need holography to help simplify the life of all of the equations. But it is fun to consider what we could do with holography. Like, what else can we apply it to? Because it does seem like such a useful, magical tool to me.
And actually, now I have a chance to mention this because I focus not on entanglement, but also the quark confinement in my PhD. And holography really is one of the biggest tools and possibilities that we could solve one of the Millennium Prize problems, that being the Young-Mills existence and the mass gap. So just to throw that out there, that nice. This is a $1 million question.
Yeah, I feel like we're opening so many avenues for future conversations as well. Yeah. Fun question by Paula here. I love these crazy thought experiments you're coming up with. If I entangle two particles and then move one at time dilation speed so they are years apart in age, but now physically near, will observing one reveal the other at a different time? That's a nice question. So just to answer that, you don't really measure the time of the particle or the age of a particle, especially when dealing with photons, because then you have the fun thing that photons don't actually experience time. But what you measure here is different properties like the spin, and things like that would not be affected by how long a particle has been traveling. So you could time dilate them, measure them. It doesn't matter. You can have one particle traveling at the speed of light, one staying still. They will still be entangled if they were entangled initially.
Yeah. So what you really want, if you want to figure out, okay, how can I use entanglement to something, you need to know, first of all, what kind of properties from a particle you can extract with entanglement. That being spin, or in qubits, the state, something that can be measured from the particle, not from the surrounding of the particle. And then you can think, if I can, those crazy thought experiments, in what kind of situation would they be useful?
Nice. So we have a question here, and I'm going to rephrase Scott's question into a way that I want to ask the question. You mentioned quark confinement, and I'm not sure if everyone knows what quark confinement is. So do you want to just tell us what you mean when you say quark confinement?
Yeah, so quarks are those cute little things that are tied together by the strong interaction and make up some of they are elementary particles. Yeah, here they are. Here's the table. And they make up particles like neutrons and protons. And the fun thing is that you cannot ever find a single quark. They always come with another one. So there is no single quarks. And then a question rises also, why are the masses of quarks what they are? And these also are questions that we really do not know. We don't have an answer. And really fun, usually when you try to pull two quarks apart from one another, you end up creating a new pair of quarks in the middle, because the amount of the force that the strong interaction creates in between comes more energetically better for nature or the system to have another pair of quarks, because the force grows so strong. So even if you try to rip apart the two quarks, you cannot separate them. You just create a new pair. It's like trying to rip apart a rubber band. It's just the forest grows stronger and stronger.
Yeah, I think that's such a nice concept that, you know, you have this quark and anti-quark, sorry, you have two quarks together. You just try to pull them apart, and you need so much energy that the universe is just like, no, we're just going to create more quarks for you now. It's kind of like if you try to cut a magnet in half, you know, you have a north pole and a south pole of a magnet, you cut it in half, you're not going to have a north and a south, but each magnet will then have a north and a south pole.
Yeah.
And it's just similar when you're trying to pull quarks apart. It's just like, no, can't do that. Just gonna keep them all together. And that is so cool. And the fact that we don't know why this happens, or we know why it creates more, it's just energetically favorable. But why are there quarks together? This is something we don't know.
Yeah, and actually in holography, when we do this mathematical trick, we have entangled states, and then we do the trick of mathematically going to the gravity side, and then we see that, oh, okay, this is also the thing is, people ask me which field I am. I'm like, well, quantum field theory, gravity, also string theory, because all of those three kind of come together in holography. So I'm like, whichever you want. Like, we can talk any of those. We can have a string theory day here. But
you are opening yourself up to me asking you back for string theory day, because I do get a lot of questions on string theory. So you're opening yourself up to be invited again for string theory.
Yeah. So remember when I said that we do the trick and we put the field theory on the boundary of this gravitational bulk? You can think of that when you have the boundary. You can think of this mathematical space as a string hanging from the boundary. And then you can use mathematics of a string theory to describe it. And what happens is that you end up describing a quark-antiquark pair. So somehow you start with trying to explain entanglement. You end up calculating the potential between quark and antiquark and explaining the confinement. And that's really what I do. So it's really like you start a story, you end up in a whole another topic.
Definitely unexpected direction there. Comment by Paul here: if you can't have a quark by itself, maybe two quarks is more fundamental than one. I mean, we use the example of two quarks, but you can also have three. In fact, the proton has three, the neutron has three. So would you make it fundamental to have two quarks, to have three, to have more? The quark is the fundamental particle, because we always talk about fundamental particles as being the smallest building blocks we know of. So two quarks you could break down into separate quarks, so it wouldn't be as fundamental, but it is more naturally occurring to have two or three quarks instead of just one quark.
Yeah.
Okay, so there's a lot of directions where we could go here. There's something else that I'm definitely saving for a future conversation, which is how we go from quantum entanglement to the idea of the many worlds interpretation of quantum mechanics and multiverse. But that is something that I think requires a whole hour to discuss.
Yeah, maybe another guest also.
Yeah, we won't suddenly jump into the many worlds interpretation of quantum mechanics. I'm just dangling this as something that, if there's interest, let me know if you want to hear about this in the comments. If you do want to hear about this, I can try to put together a stream about the many worlds interpretation of quantum mechanics, because that's also super fun and super crazy. Now, we are approaching almost the end. Before we end on quantum entanglement, is there anything else you'd like to tell us about quantum entanglement?
No, I mean, I think we covered it. And if I start something new, we're going to have to take another hour.
Yeah, we'll take another hour. Yeah, so I hope we've been able to answer everybody's questions here about quantum entanglement. If not, feel free to ask again. I know, Scott, at some point you said you did have a question that might be too long to type. I'm just going to fix you because you've frozen, so let me just take you off and back on. So, Scott, as always, you know, you can reach out to me on Twitter if I wasn't able to answer the question the first time. So do reach out. I feel bad for Gabby. Diana did pepper on the ridiculousness of my comments. I didn't tell you that's ridiculous question, but he some questions. I'm seeing the video frozen on my side. Please let me know if anyone else is seeing the video frozen, because I'm not sure if it's on my side or where the.
Yeah, you're frozen to me, Diana, as well.
You see yourself fine?
No, I'm frozen too.
Okay, then let's just do a hard reset. Yes, wait, are we back? I think we might be back. Oh, we're still now I see everyone frozen. Okay, so I am just going to do a very quick graphic server restart just to try to fix this issue. Let's see if this fixes it. We're back now, and I think we're no longer frozen. I'm not sure what was happening there, but it appears that we're both back now. Okay, so also apparently my connection to Twitter has just been disconnected. Never mind, we don't need that anyway. Okay, so we're both back. Hopefully you're hearing us and seeing us better now that we've done this hard reset. So we've talked a lot about what Haley works on, about quantum entanglement, about all the fun things. Scott, please let us know if you, or anyone in the comments, do let us know if you can hear us properly now. We talked about all of these fun work-related things. But in addition to being a very talented scientist, Haley is also an incredible artist, and I was very happy to see some of Haley's art. So Haley, please tell us a bit about your art, and if you want to show us anything, now is the time to do so.
I mean, I feel like this is my opening to the world and getting new customers, because I do have a gallery online where you can see the artwork and oil paintings mostly. So
if you have a link, feel free to drop it in the comments.
I will find it, but yeah, I do very classical artworks, and also very classical frames, as you can see behind me. They're like this kind of frames. So
let me just put you full screen here. Apparently we're still offline for people, so I guess there might be some type of outage at Happs. We're just going to keep going, and hopefully it will reconnect at some point. So I'm just going to put you full screen, taking myself off, if Happs responds to what I just did. Okay. So now you can show us your art.
Yeah, I will put the link in the chat, and that's kind of my gallery online where you can see the art. Most of them are sold already, so sadly, but I do paint, and if you ever want to ask a painting, of course, I would only paint for people in Finland currently, because shipping paintings is painful.
Okay, we seem to be back now. Don't know what just happened there. Sorry about that. There was a bit of a downtime. Hopefully we're back and everyone can hear us again. So in case you missed it, Haley was just telling us that she's a classical painter. And I like that your work is quantum, but your art is classical. I'm very amused at that. So the link you can see here in the comments is the link to Haley's gallery. Do check out her art. You can find it all there. And Haley does take commissions, but currently only to Finland because shipping's expensive. But maybe you're going to get lots of people asking now, and you might have to expand your market.
Yeah, I may have to. Yeah. I mean, if you have some very beautiful picture of yourself or an item or something, I might just paint it because I want to paint it.
So awesome. If anyone wants to reach you, how can they reach out to you? You're not on Twitter, right?
No, but should I give them my Instagram?
If you want, you can drop your Instagram here in the comments as well. If anyone wants to reach Haley and can't, you can message me on Twitter and I can reach out as well. Mine never came back on. You had to relaunch. Okay, so if we're still frozen, obviously you won't hear this. If you are frozen, just refresh the page. So you want to follow Haley Taco on Instagram for art and cool stuff. Hey, Georgia, great to see you. Thank you for stopping by. For anybody who doesn't know Georgia here in the comments, you should absolutely be following Georgia. She does amazing, amazing streams about humans and wildlife, studies bats, is also an avid climber, I learned recently. Which, Haley, this gives me the chance to ask you, what is your favorite thing to do?
Oh, well, to climb. I have become known as the person in our office who asks everybody to climb, and the climbing center that I'm a member, they give me free tickets so that I can give them to people, because I always bring new people in. So I'm that person, and I think, Diana, you cannot say no to that now.
At some point I will join you. I will at some point, not soon, but I will join. But yeah, you're the person who asks everybody for rock climbing. I'm the person who asks everybody for Happs streams. So I do want to say thank you to you for being the first person from the new group to join, first person in Helsinki to join me. I'm very happy to have you here. And now you can help me convince others. Big thank you to you for volunteering this topic. It's been great fun. Thank you to everybody in the comments for the fun questions, the fun topics. Georgia wants to go climbing with you or share climbing stories with you, Helly, because Georgia lost climbing as well. I learned recently with some very scary climbing videos. Okay, so anything you want to say before we wrap up the stream?
No, I'm more than happy to come back to talk about string theory or holography even further.
So we're going to do a whole stream about string theory at some point. Maybe we could put together a panel, have you, maybe somebody else in the office as well.
Oh, my supervisor should, because he is the string theory king in our
Sure, so I'll tell him that you volunteered him to join me.
I don't want to lose my PhD position, so rather not.
I'll kindly ask him if he wants to join for a discussion on string theory. Okay, and Scott has basically the same comment I made. Climbing doesn't scare me, it's the slipping and falling that is the scary part. I'm with you, Scott. I like my feet on the ground. Yeah. I will go climbing at some point because Hilly is very convincing, but I'm not a fan of not being on the ground. Okay, so big thank you to you, Hilly, for joining. I am going to take you off screen, but please stay here and then we can chat afterwards. So thank you to you for joining.
Yes, it was really fun. So bye-bye, everybody, and have a great night.
Awesome. So again, thank you everybody for joining. Thank you for the comments. Thank you for the awards and for the great questions. It's been great fun. I hope you all managed to figure out the change of time zone. And I'm not sure when I will be back online. I'm not sure if I'll be doing a stream next Sunday because I might be taking a slight break. I will try to be back soon, but I can't commit to next Sunday. As always, if you want a notification for when I'll be live, be sure to hit the subscribe button here on Happs. I do announce all of my streams in advance. So if you subscribe to me, you get about at least 24 hours notice as to when I'll be live next time. So I will be back very soon, not sure when, but I'll be back soon. Now I'm also apparently going to plan a stream about string theory. So thank you everybody for joining. I hope to see you all again very soon. And in the meantime, stay safe and take care of each other.